Okay, good morning. Welcome back. I hope you had a good weekend. And let's get started. Any questions before we start? Okay. All right. So we're going to continue with our discussion about kernel methods. Okay. So we were looking at kernel methods last time, right? And the basic idea behind kernel methods is just that they are, so whenever in any machine learning algorithm, right, if you see that your data, your input data, the X that you're interested in, occurs only in the form of an inner product with other X's, right? So we saw that how that happens in regression, linear regression, by changing the form of our learning method, right? And the same thing you'll notice also in the case of support vector machines later today. So the idea is that whenever X just occurs in the form of an inner product, so inner product or the dot product is just a way of computing similarity between two objects, right? Which means that you can replace that with any other function which also computes the similarity between these pairs of objects, right? So instead of the dot product, which is one way of computing similarity, we can use something else. So that is the essence of kernel methods. So that function, that similarity function, is called a kernel function because it allows you to do these primitive operations on every pair of objects and then use that in a larger machine learning algorithm, right? So that is the idea. Now, why we want to do that? So we motivated that in two ways. One is the scenario in which your X is not easy to represent as a fixed length vector, right? Because all of the linear models that we have seen so far do perform this operation of W transpose X, which essentially means that you have a weight vector and an input vector and you're doing an inner product between them. So if your data is not easy to represent in that form, but on the other hand, if you have an easier way to compute similarity between your data objects, so let's say your data is just a blob of text, then or graphs or strings or whatever, right? If you can compute the similarity, you can apply kernel methods to work with that kind of data. So that is motivation number one. Motivation number two is that the effect of kernel functions is essentially trying to so we saw that last time, right? So what happens is that if you think of nonlinear regression or any nonlinear method, one way to do that is that you take your input and you apply a bunch of basis functions to that. We did that for our programming assignment 2. And then what happens is that because you are, and if your basis functions are nonlinear in their nature, then what will happen is that once you map your data into this new space, new p-dimensional space, by applying p basis functions, the lines that you will learn in that p-dimensional space will look nonlinear in your original space. So that is the idea, right? Now the same effect can be obtained by applying kernel functions to your X. So instead of explicitly mapping your X from D to P by applying P basis functions, you could instead use the kernel method sort of philosophy and replace your X transpose X, the inner product, with a kernel computation, a similarity computation, and it will have the same effect. Now some can argue that it's not really giving us a benefit, right? We could have, instead of that, just used explicit basis functions and mapped into high dimensional space. Now the benefit of those gets more sort of clear when we look at this one particular function, which is called the radial basis function, right? So radial basis function, so let's look at this one, the one in the middle, right? So what radial basis, this similarity function does is that it computes similarity between a pair of objects, xi and xj, in this form, right? So you're computing xi minus xj, the Euclidean norm, and then putting it in exponent. Yeah? And we saw that what is the effect of sigma on this, right? So sigma kind of denotes the width. So the idea is that every x, you're trying to compute it with other x's, and the similarity sort of drops off as you go far. That's because of this exponent here. And how fast does it drop or how slow it drops is given by this sigma. Okay, so now let's look at RBF kernel. The one beauty of RBF kernel is that it essentially means that you're mapping your data into an infinite dimensional space, which is pretty cool, right? Because the idea is that you have your data and it might be very hard to separate by a line in your original space, and you map it into an infinite dimensional space. And there, it seems more likely that you would be able to draw a line or a plane to differentiate them, and when you bring it back, it would look nonlinear, right? So that is the beauty of RBF kernels. And so the first thing we want to do this morning is try to see, why do I say that RBF kernel essentially means mapping inputs to a infinite dimensional space. It's a very interesting result, and just makes use of Maclaurin expansion. So we talked about Taylor series expansion earlier in this course, right? So the idea is that if you have some function of x, fx, you can perform a Taylor series expansion around any other point, right? So fx can be expanded with respect to any other point using the Taylor series expansion. If that any other point is 0, then that's called a Taylor series expansion, all right? So there are a lot of interesting Taylor series expansions of different functions, and we use them because they help us sort of approximate. So the idea is that you have some function, you can approximate it by its Taylor series expansion, and because the Taylor series expansion will only have quadratic terms, so you could sort of work with that more easily than with the original function, right? So the Taylor series expansion for e power x is given like this. It's summation, so it goes till infinity, so it's an infinite series, right? E power I, oh sorry, not e power I, 1 over I factorial x to the power I, right? So essentially, if you have right, so for example, you can write it as 1 plus x squared over 2 plus x cubed over 3 factorial, and so on till infinity. All right, so we are going to make use of this result, right? But that is something that I'm assuming that you know already. Okay, so now let's look at it. Right. So what is the k, the RBF kernel, right? So RBF kernel says that k between any 2 points xi and xj is given by exp minus 1 over sigma square xi minus xj, the L2 norm, right? Now I'm going to assume for this sort of for this result, we assume xi and xj are in one-dimensional space. So, and you can extend it to d-dimensional space. So that means that k of xi comma xj can be written as exp sigma square, right? And just for the sake of not writing too many things, I'm going to assume sigma is 1, so the density is 1, but that doesn't really matter because sigma is just a constant for us, but that will just help me write things a little easier. So I'm going to assume that this is nothing but minus of xi minus xj square, right? So that is easy, and then I can expand it and say that this is equal to minus xi square minus xj square minus plus 2xi xj, right? And then I'm going to just open this. This is exponent, so this will be exponent of minus xi square times exponent of minus xj square times exponent of 2xi xj, right? And then what I'm going to do is I'm going to expand this using Taylor series expansion, and this is going to become exp minus xi square exp minus xj square, and then this could be written as just summation from I equal to 0, well, not use I, k equal to 0 through infinity, right? 2xi xj to the power k, right, divided by k factorial. That's just a simple expansion, right? And then what I'm going to do is I'm going to bring these inside and just do like this. So because they do not really depend on k, right, these terms, so they can be brought inside. And I'm going to split this, so I'm going to say exp minus xi square over times exp minus xj square. Okay, and I'm going to split this into two terms. One is going to be under root 2 xi xj k by 2, right, which I can write times root, and then the same thing again. So basically I'm splitting this to the power k into two products. K factorial to the power k by 2. All right, so that is sort of easy. And then what we're going to do is we are going to multiply this here and that there. Right. So this could be written as, so I'm going to write this as 2 raised to k by 2, right? And exp minus xi square times this part, so xi, just the xi part, k by 2, times exp minus xj square, and then just the xj part. I'm sorry, why? Oh, no, sorry. This is to k by 2. These are sorry about that. So just the root 2 comes here, and this root 2 comes here. This xi to the power k goes with the xi square, and the xj to the power k goes to xj square. Made a mess. All right. So this is sort of the result that you can just derive using this derivation. Sorry, I made a mess here, but all we did was just rearrange terms so that all the xi terms go here and all the xj terms go here, right? So the main thing you want to see here is that this looks like, so this is like a product, right? So essentially what's happening here is, or a sum. So you can write it as, it's almost like if you had like a long vector with infinite rows, and in each here you had 2 to the power 0 by 2 exp minus xi square 0 factorial xi 0, right, this part, times 2 to the power 0 by 2 exp minus xj square factorial xj to the power 0, right, and so on. So there'll be a term with 1 here, term with 2 here, and until infinity. So here it will be some very large number, 2 power n by 2 xj to the power n. Here is xi to the power n, and then so on till infinity, right? So this is sort of the same thing. So it is these quantities in a whole vector, column vector, and then you sum it up. So then you sum it up outside, right? So that is a fact. Now what you can see is that that looks like if you had two vectors, this and this, and you took a dot product of them. Because if I have two vectors like this, then if I take a dot product, that will be multiplying each corresponding points and adding it together, right? So this is same as saying that you had two long vectors. One was 2 0 by 2 exp raised to raised to xi to the power 0, and so on till infinity, and the dot product of that, so transpose, is this. Right, which essentially means that you took your xi, right, and you created these infinite values out of xi, right? You took xi, then you replaced it with this, with this, with this, and so on. So you took infinite basis functions in some way, right, and applied them to xi and created a new basis function expansion, which is of infinite length, right? And the same thing you did for xj, and then you took an inner product of that. So, which essentially means that we map this xi into an infinite dimensional space where each coordinate in that space was this, and then so on. And same thing we did for xj, and then we took an inner product. So that's why we say that computing the RBF kernel, right? So remember what we started with. We started with this part. So when we computed the RBF kernel, it is the same as first mapping the data into infinite space and then computing the dot product in that space. So that is the idea. So that is why RBF kernels are very powerful, because all they're doing is not all, but what they're doing is they're mapping data into such large space that it's very likely that you would be able to draw a line there. All right? Any questions? Yes. Right. Yeah, so the point is that what happens with a kernel function is that if you apply any kernel function, it essentially internally it maps x to x to some space by applying some internal basis functions and then does a dot product. But what kernel methods allow us to do is that not worry about that explicit mapping. They say, because eventually you just need that dot product in that higher order space, right? That you can compute just by taking that kernel function in the original space, right? So the effect is that when you apply a kernel function like so when you apply a kernel function, so for example, if your kernel function was just a square dot product, right? Which means that what you did was you first mapped your xi into this new space and xj into this new space, right? And then took a dot product there. So that has the same effect as using when I was trying to show you how to draw circles, right? But we don't explicitly do that in kernel methods because we don't need it, right? Because eventually we would just be taking a dot product in the higher order space, in this space, which would be same as just applying the original kernel function. So you don't have to worry. So for example, in Gaussian kernel, right, as I said, you're actually mapping things into infinite space. Now we can't do that, but that's just what happens internally. So the beauty of kernel functions is that you can come up with new kernel methods, new kernel functions. All you need to ensure is that they're valid, right? Remember, we talked about the validity of kernels, which is that they need to be symmetric, they need to be, the kernel matrix that you get should be positive semi-definite, right? As long as that is ensured, you don't have to worry about what were those basis functions that would lead to the same kernel operation. All right? Okay, any other questions? Okay, good. So let's keep moving, right? So now we have this beautiful kernel. Now we'll see, okay, one way to use this kernel function, okay, which is called a kernel machine. So the kernel function, one thing you can notice is this is another use of kernel functions. You can use these kernel functions to actually generate new features. So for example, there is one particular type of machine learning algorithm called radial basis function network. What happens is that you first choose some points in your data set and we say these are my representative points, okay? And then for every training data point, you compute a kernel function with each one of these representative points. So let's say you had 4 points like that. So what will happen is that you will compute your kernel function of every input point with each one of these 4 points, right? So now each of your point is now in a new space, in a 4-dimensional space, right? And now you can apply things like linear models or whatever on that data, right? So what happens with that is that you can use it for any type of data now, right? Because as long as you are able to find representative points and you are able to compute a kernel function, you can use it for any type of data point. So for example, in the radial basis function, we actually use clustering, and we'll talk about clustering maybe today. It's essentially that you're trying to, you have some data and you just try to find 4 or k points that are very representative. So that one way to do that is by doing clustering, right? And then what you do is every new data point or every training data example is converted into this k-dimensional space by applying this kernel function with respect to each one of these centroids, right? And now suddenly you have a feature vector representation of your data. So think about it this way: if you had x, which is not, which is not a traditional vector, right? Let's say x are strings. So what you can do is you are given this bunch of strings. You can take a few strings that you think are representative. Maybe some expert gives it to them, or maybe you run some clustering to get them, right? And now you can take these strings and a kernel function, right, and apply it to every training string, right? And you can get, for every string you will get 4 values because you had 4 representative strings. And then you can apply any method to that, any linear method. So you can apply logistic regression, or even any other classifier, right? Any classifier perceptor on the support vector machines, right? So that is the idea. So one particular instantiation of this general framework. So this is a general machine, right? You can apply it to any type of data as long as you have a way of computing the k centroids and you have a way of computing the kernel. So you have some kernel function. If you choose the kernel function to be our RBF kernel, then that machine is called radial basis function network. All right. So what you do is you choose some mu i's, which are your centroids, and these could be chosen using clustering or random selection. Maybe you just select a few points, and then you apply radial basis function and apply it to the data. That's called the RBF network. All right. So in fact, in my demonstration page for kernel methods, I have that here. So RBF kernels are nice because they let you sort of learn these nonlinear boundaries, right? Because they are going to project things into this higher order space. So let's look at this. So let's say this is my data. Right. So I created this challenging data set, right, which has 2 types of points, but they are in these 4 blobs, right? And the problem is that they are, it's not easy to separate them by a line because they are what we call an XOR example. So you can never draw a line that separates them. But instead of that, what I'm going to do is I'm going to define a radial basis function kernel, which is defined as this, as we have seen before. And I'm going to use the centers of these blobs as our representative points. Okay, so 4 points. The way I generated these blobs was just assuming that each one of them is a 2-dimensional Gaussian, right? And then I sample points from that. So each one had a different mean. So I can choose those means as my representative. So I'm cheating a little bit because I already knew what generated this data. But this is just for illustration. In real world, what you would do is you'd run clustering on this data and get 4 sort of centers, which would give you the same thing in this simple example, right? Now what happens in this example is that I do these kernel computations, right? So for every data point that I have, what I do is I compute the kernel function, that RBF kernel, between my data point, which is my xji, and one of the representatives, so mu1, mu2, and so on. So every time I get these, and then I choose sigma. Sigma is that kernel width, right, in your kernel function here. So now I can apply, now what I have is kx, right? So kx is going to be if my data had n points, then kx is going to be n cross 4 because I have 4 points now. And now I can fit a logistic regression model to that, right? And the w that I'll get, of course, will have 5 values, right? Because it'll be intercept and then 4 values for my 4-dimensional data. Then I put it back into the original space. Now, how do I do that? Essentially what we did in your QDA, LDA business, right? So we consider the whole grid, and then I evaluate the function on each and then say, is it positive or negative, right? And once I do that, this is what I get, right? So this is sort of why RBF kernels are so nice, is that they are able to learn this sort of boundaries with this. Now you could do something else. For example, instead of using RBF kernel, you could have used some different kernel. Example that that x1 square, x2 square, square root of x1, x2, that kernel, and that would give you a different curve, right? RBF kernels will always give you these nice globular curves because they are sort of measuring distances in a squared form, right? That's the expression over here. So, but if you change it to something else, you will get some other aspect. But this is sort of a general methodology to compute, to come up with a new kernel machine, right? Two things you need. One is how you compute your kernel computation, so you can replace this with something else. And one thing is that how to choose the muse, right? Now here I just used muse because I knew these were the muse that were the means of those Gaussians. But you can use some other method to do this, right? That's it. And that way, you have a new kernel machine. Any questions so far? Yes, go ahead. Okay, so that's a good question. So the question is that if you are applying, you doing this infinite dimensional space thing, and then learning there, is it not overfitting? And the answer is yes, right? For example, here, I think you are overfitting, right? But so then what you have to do is you have to control that overfitting in some other way. So in SVMs, we'll look at that. So what happens is that essentially it's the same idea, right? So you have data in this high dimensional space. You will have to apply some regularization there so that it does not overfit. In this case, we are not explicitly controlling for overfitting. So this would always give you an overfitting answer. So if I changed my data, made it, all kinds of points all over the place, and some of them were positive, some of them are negative. If you do this whole business there, it will overfit a little bit. But one way to control the overfitting in this case is by this number of centroids that you use. So what will happen is that, yeah, maybe I should have that demonstration at some point. But here, so this is another parameter of this RBF network, right? How many centroids do you need? So if you choose, let's say, one centroid, okay, so then what you would be doing is you would be mapping every data point into one-dimensional space. So then your model will be very simple. But if you increase that k, if you make it 4, then it will start making balls. If you make your k to be the same as the number of training data points, that means that you are replacing every data point by n. Let's say you had n data points, n kernel computations. Then it would be too much overfitting. Then what will happen is, so the effect of that will be here, is that let's say you had things mixed up. You had some red here, some blue here, everywhere. If you choose your k to be very large, then it will form like small balls around every point. And that's how it will, so there will be too much overfitting. But by choosing a smaller k, you could still control it. Like here, because I chose 4, it comes up like this, right? But if I choose my k to be very large, then you will see much larger number of sort of values. So for example, I'm trying to see if I can do that. So for example, if I say my muse are just my x, right? So muse are x, and then do this whole business. It's going to take longer because you're going to do a pairwise computation. It didn't change much here because the data is very simple, right? But if I do something, if I change my original thing, I make them mix with each other, right? Let's see with this guy. Aha. So now you see that things start getting over, sort of more non-linear, and then you can play around with this, make it 2. I think this is going to just things are going to get mixed up. And now if I do this, because the points are now going to be outside. So now you see that it's even more sort of overfitting the whole thing, right? So that is the effect of the number of centroids that you choose. So in RBF machines, like all these kernel machines, the number of centroids that you use sort of directly controls the overfitting aspect. Any questions? Okay, very cool. All right, so let's keep moving now to our next topic, which is how does this apply to support vector machines, right? All right, so that's actually part D2. And this is going to be a very short part. So the idea is that support vector machines, and we didn't look at it too carefully last time, is that inside the support vector machines, when you do the learning, you will see that all your x's also occur in inner products, all right? So if we go back to, this is just a recap, right? This was support vector machines, we did this last time, and this was the original function that we wanted to optimize on. We changed it into this dual formulation, and then this is what we got, right? We said W is essentially alpha n, y, and xn when we solved the first part of that Lagrangian, and the second part, basically we said we're going to solve this for alpha, right? So I hope you all remember this. This was just fresh from last Wednesday, right? But let's look at this equation a little more carefully. So we want to, actually this is a little incorrect equation. So here we are only trying to maximize this LD with respect to alphas because there's no W or B here, right? So if you look at this very carefully, what you see here is that in the whole formulation, the only place where you get x, m, and x, any x, is in a product with another x. So whenever you see a x, it is stuck to another x in some ways, right? So that is where you can apply kernel methods, because I can now replace this inner product with any k, x, m, comma, xn, right? And that is why support vector machines are, what should I say, are appropriate to apply kernel methods on, right? So you can get kernel SVM. So all training examples occur in dot or inner product. So that is one part. Even in the prediction, and this we saw last time, was that when you now want to find the prediction for a new data point, what you see here is that W, right? So we compute W transpose X plus B. Now you can replace this W by this value, right? Which means that W transpose X goes out and you get this. And if I rearrange this, even to get the predictions, you need xn comma an inner product, right? Which means that you never need your training data or your test data by itself in SVMs. Every time you need your training data or test data, you need it to be coupled with another data point. So that's the classic application for kernel methods. So you can simply replace this dot product with a kernel function, and you will get a kernel SVM or a nonlinear SVM, because that is the effect of applying nonlinear kernels. So I can replace this with a RBF function, and I'll get a RBF SVM, or any other function, I'll get that kind of SVM, all right? So that is the idea. Any questions about this one? So that is another beauty of SVMs, is that you actually never, so if you take up any implementation of SVMs, right, what you will see is that they will never give you W, because you don't really need W. All they will produce are these support vectors, the alphas, all right? Sorry, not the support vectors, this Lagrangian multipliers, because that's all you need to learn to predict. You never need W here. They'll give you B because you need the B part, but they'll never give you W because you don't need it. And in fact, you'll realize that if you are using an RBF kernel, right, which means that you're actually mapping your data into infinite dimensional space, which means that you would have, so your data is a vector of infinite dimension, that means your W will also be a vector of infinite dimension. So there's no point of giving an infinite dimensional W, right? So they will not give you W, only give you alphas. And another cool thing about this is that if you remember last time, that alphas, right, not all alphas are useful. The only alphas that are useful in support vector machines are the alphas corresponding to the training points that lie on the margin or inside, basically the support vectors, right? Which means, and typically what happens when you're applying, when you're learning support vector machines, is that you get very few support vectors, which are the ones that define the margins. Everything else actually is useless, right? Which means that when you store your support vector machine, right? So what will happen when you do your SVM is that you will learn it, right? And then you'll probably store it in a file. You will only have to store a few alphas, not all of the alphas, because if you remember the KKT condition number 5, what that tells us is that alpha will be 0 for points that are not on the margin, right? Which means that you only have to save the non-zero alphas, which will be much fewer than the all of your training data. Which means that SVMs allow you to learn these compact classifiers, which are not only good in terms of differentiating data, but also easy to store, right? Which becomes an important issue in many applications. Any questions? All right, so this is actually a very crucial turning point for us, or at least a transition point, because from now on, we are going to look at a new topic. Let me bring it up. This is part A of the course, right? Which basically is, so before we start, I want to give you a little bit of let's step back a little bit. So far in our course, since we started in January, right, we have been looking at the problem of learning some function of x that gives you y. So every time you had some y, which was your ground truth, and you had some x, which were your features or attributes, and we wanted to predict y given x, right? So we looked at regression in which y was continuous. We looked at a lot of classification methods in which y was binary or it took a few values, right? So now, so this whole area of learning is called supervised learning. The reason it is supervised learning is because you're always given some training data, right? And in the training data, you are given some ground truth, right? So that's sort of a supervision that is given to you. And then you learn from that data to apply to a new data point, right? There's another type of machine learning, another class of machine learning problems, which are called unsupervised learning, in which all you're given is some data, all right? You're given some data and you're asked to sort of give some understanding in the data, okay? So the one type of problem there is called clustering. So I mentioned that earlier as well. So the problem of clustering is essentially that I'm giving you some data points, right? Let's say I take all the students in this class and I extract some features for those students. And what the clustering algorithm is supposed to do is to partition these students into different groups such that each group is similar to each other, right? Very easy to understand. So maybe all the, students who sort of wear blue shirts to class become one cluster, and students who wear red shirts become another cluster. Depends on what your features are, of course, but that is the idea. So let's sort of make it a little more concrete. And then later on, I'm going to sort of discuss clustering in a slightly different way. So I like to consider all these methods as what I call latent variable models, all right? So there is some latent means hidden. So you'll hear latent a lot from me now on. So latent essentially means that latent variables is that you have some data that you observe, right? But they all have some attribute that connects them. But that's something that we don't know. We haven't seen it. And we want to infer that from the data, right? So clustering, you can think of that latent variable as your cluster index, right? So let's say we know that this data has, all these data points belong to one of three clusters, right? So 1, 2, 3, these three numbers are the latent variables. We don't know which one belongs to what, and we want to find that. So that is the task of learning, of clustering. And then later on, I'll show you other models that are sort of, they all fall under this general class of latent variable modeling problems, all right? So first, let's look at clustering. In fact, let's first look at a little more general form of clustering. So let's consider an example, right? Let's say you are a magazine editor, right? Let's say you're all Nancy Gibbs from Time magazine, and you're sitting at your desk and you want to produce the next issue of the magazine, right? So let's say basically let's make it very simple. So let's say all the editor does is that she tries to figure out what articles to add to this whole magazine, right? So what she would do is that, let's say in your magazine, there are only 4 types of articles you can have. So you will have an assistant editor for each one of them. Let's say politics, health, technology, sports. And then what you will ask each one of your assistant editor to do is send in certain articles from each class, and then you'll put it together and, hey, here is your Time magazine for this week, right? That's easy. What happens on the other side is, let's say if you're a reader, right? You get the Time magazine. Now you want to infer, after you read the article, which assistant editor had sent this, right? Because let's say in the magazine it doesn't say. Let's say they hide that information, that what type of article this is. Then you want to figure out which type this is. So that is sort of the task of clustering, right? So each article has a hidden type or a latent variable associated with it, and now you want to assign the type to each article. So that is sort of the problem of clustering. Can you group these articles by type? Actually, this simpler problem is simpler because here you're not really going to. So there are two things, right? So one problem could be that given a new article, so I'm reading this magazine, right? Let's say this is my Time magazine. I'm reading it. I see this article. One task would be, I want to figure out, is this article sports or health or politics, right? That's a little more tougher job. A simpler problem could be that I read all the articles and then I say, all these articles are one type, all these are another type, and these are another type. So I have not really assigned a semantic, I have not assigned semantics to my cluster. I haven't said that these are all sports articles. All I've done is that I've just grouped them together with the hope that all sports are together, right? So that is the task of clustering. So essentially you're trying to group similar things together, which means that there is a notion of similarity or a distance there, right? Somehow you should be able to compare objects. So that's how you'll put it together. So for example, let's say this is your data, right? Your data is in 2 dimensions. So there are 2 features that you have that define your data. And let's say this is how the data is, right? What you want to do is you want to assign colors to these data points, right? So in the beginning, you didn't have colors. Now you want to write a program, a software, which could take this data and assign colors to this such that all the reds are together, all the blues are together, right? So if you have a program that colors half of this red and half of these red, then probably that's not a good algorithm, right? This is sort of the ideal case. So how do we do that? All right. So one algorithm to do that is what we call k-means clustering. K-means clustering, the task is, as I said before, right? You're given some data, you want to figure out which data points are together and which ones are, so essentially which data points are together. That's it. And actually it makes it a slightly easier problem by saying that it also needs how many clusters there are. Right? This becomes a very typical issue in clustering, right? So for example, here, what k-means clustering expects you to tell it is that there are 4 clusters to be learned, all right? So what happens is that if I say there are only 2 clusters to be learned, you can still apply k-means clustering, but then it won't give you this result. It will probably color these 2 red and these 2 blue, because that's what you asked, right? So it's kind of dumb in that way. It does not automatically learn how many clusters these are, and that's actually a pretty hard problem, right? So here we are assuming that we given some n data points and we want to cluster it into k clusters, right? So the algorithm is very simple. Actually, it's maybe the simplest to explain. So you start with some k randomly initialized points in this d-dimensional space. So for example, let's say here, what you would do is, let's say k is 4. So you'll choose some 4 points randomly, right? So they all could be here, or they all could be here, or if you're lucky, maybe one is here, one is here, one is here, one is here. But there's no guarantee where is what is where, right? So there's random. We call them cluster centers or centroids, right? Then what we do is we take each data point and compute its distance to each one of these centroids. And then we say that, okay, a data point is assigned to the centroid which is closest to it, right? So we compute the minimum distance for every data point to each one of these k centroids and find the k that gives you the minimum value. And then what happens is, then we revise our centroids, because now what will happen is that some data points will belong to the first cluster. Now what you do is you recompute your centroids, and that would shift, right? And then you keep doing that until things don't change anymore, right? It's a fairly sort of straightforward and very easy to, apply method, right? Any questions about this one? We'll see a demonstration by the end. Right, so that's a very good question. So are these part of your training data or not? So actually, they need not be. They need not be part of your training data. So they could just be part of this space that spans your data, right? But what happens in many practical applications, it's easier to select points that are already in the training. So think about when you're implementing this, right? Let's say your data space is 100 dimensional, right? So D is 100. First, you have to find n points from this 100 dimensional space. You could sort of sample from this 100 dimensional space. It might be tricky. So instead of that, what you could do is you could just pick 100 points from your training data point. But there is no necessity. I mean, there's no requirement like that. All right? Any other questions? Okay, so let's quickly look at a sort of an example and look at that, right? So this is sort of a very simple k-means demo under clustering demo notebook. So here what I do is I create 4 data points using my favorite strategy, which is I generate 4 Gaussian sample from them. NP is not defined. So this is how the data looks like, right? So I just took 4 means and then sample points around it. And I just randomly gave them some labels, sports, politics, that doesn't matter. Now what we do is, first we pick 4 points. So here we are going to assume that we are picking 4 cluster centroids. Oh no, here actually, why am I doing 15? So let's say I pick 4 cluster centroids, right? And here I'm doing what I said, right? So I'm not picking from the whole space. So your point was that we could have picked data from this space, right? Which is acceptable. Here I am picking data from among these 100 data points I had, or whatever data points. So these are, let's say, the random centroids that I get. Then next thing I do is, in this loop, and you'll have to go through this later on, is every time, basically I run k-means. So every time I compute the distance between your data points, and then I keep refining my centroids. So what you'll do, see here, so here is how it got started, right? So I had 4 centroids, 2 were here, 2 were here. The first time I assigned points, right? So the first time what will happen is that these points would say, hey, we belong to this centroid. These points will say we belong to this, these points will say we belong to this, and so on, right? So all of these points belong to this centroid. Then you refine your centroids. Then what you would do is you'll take all of these red points and recompute your centroid for this part, right? So what will happen is that this centroid will shift this way because now you have more points over there. So that's what you see. Right? So the centroids have been recomputed and shifted. One blue one gets lost here. And then you reassign the points. So now what will happen is more red points will call this as their representative, right? And then you keep doing this and over and over and over again. And at some point what will happen is that all the centroids would have shifted to their natural positions, and that's it, victory, right? Of course, it also, k-means is not, it's not guaranteed to give you this result every time, because it also depends on what your initialization was. So in fact, what happens, at least in previous classes, is sometimes, let's say this is my initial centroids, right? What has happened is that if I run it, so you could come into this degenerate case where, oh, this time it worked very well. But sometimes it might not. It just depends on how you started it, right? So it's very sensitive to your initialization. So a lot of times in actual k-means implementations, you will have several tricks to pick these centroids, right? Ideally, you would want to pick the centroids which kind of follow the natural clustering. But that's sort of a chicken and egg problem because you don't know the clustering to pick up the centroids, right? So there are certain ways to do that. One way is that you can try many different versions, right? So first you try with this, then you try with something, and whichever gives you the best value, you would sort of say, that's my answer. Another way is, it's pretty interesting. So what you do is you pick one random centroid, then you pick a point that is farthest from this in your training data or in your data, and that's a second. Then pick a point that is farthest from these two, that's the third, and so on. So those are just some smart heuristics to ensure that initialization does not mess up your clustering. But in general, there is no principled way to do that, all right? So in the same demo, I've also shown you how to do this clustering on your hand digit data. So it's the same data set that we had before, right? MNIST. And if you take that data and apply clustering, here I'm using the k-means of sklearn because it's more efficient. And then you do all of this. And if I plot my centroids, right? And basically I took 10 clusters, I'm hoping. Yeah, 10 clusters. So if you look at the centroids, and basically the centroids will be vectors, then I sort of reshape it. You know how to do that. You'll see that each one of them kind of represents one of the digits, right? So these are a cluster that represents all the 8 digits, 7, 6, 9, and then it also messes things up. I think it was 2, 3, and then so on, right? So you can apply it to any data, and typically it works pretty well if your data is well separated, right? So for example, instead of this as my data set, if I just had one blob and I asked it to give me 4 clusters, it would give me 4 clusters, but they would not make any sense. But that's okay because your data didn't have 4 clusters to learn, right? So it works when your data does have clusters to learn. So for example, here, instead of taking, where is that? Oh, init centroids. So instead of taking 4, if I said, give me 10 centroids, right? So it will do this, it will do all of this business. And then what you get is just some mess, right? So you have these 10 centroids, some of the points are here, some of them are here, and they just got all squished together because these are far away. But that's the problem with k-means. It will give you what you ask it to give you, but it might not be the correct answer. And the problem is that it's sort of this chicken egg problem, right? So you need to know how many clusters there are to get those clusters. If you don't know, then it can't help you. Any questions? All right, so I'll talk to you more about this on Wednesday. Thank you very much. The gradients quiz for this week actually has problems that we looked at last time. So it's support vector machine kind of problems. So when you're trying to attempt it, you can actually do it even now because you don't need all of this for that. Okay, thank you very much.
About calculating slack, there was grades.
Right.
So you said like slack is the distance of the point from the action, right?
If it is on the wrong side,
It's on the right side?
then 0. Because remember, the slack is basically the penalty that you pay.
Okay.
If you're on the right side, you pay no penalty.
Okay. So even if it's on the wrong side, which margin is the distance from? Because I think there's like 2 margins, right?
So whichever is, so let's say if it's a positive point.